it might seem like a lot, but I want to keep going through and explain why certain things may or may not work. The nth term test would actually be mildly interesting on this one. Did you try it? You can make some progress with it for sure, but it might not be worth the effort. I don't know. There'd be a L'Hopital involved, and so I don't know. I don't know that I would just completely discount that one. It might actually be worth pursuing. Let's talk about what it definitely isn't. It's clearly not a geometric series test, right? And also clearly not a p-series because of the square root and the +1, and the fact that the numerator is an n at this point. So yeah, you might have messed around with the nth term test, and I think that could be worthwhile. But to me, the easiest of those methods we've learned so far would probably be the integral test. And so we'd want to make sure that we've mentioned the fact that this f of n equals n over root 1 plus n squared is positive. You can simply analyze that by looking at the inputs for n and thinking about what's going to happen if you do start inputting those. Continuous and decreasing. The decreasing is a tough one, maybe to see right away. The continuity, you might think, hey, is there going to be like a vertical asymptote or a square root of a negative? But based on the inputs, that's not going to happen either. Okay, so let's take a look at this from an integral test perspective. You might, I don't know, this would be a tough one, as far as looking at those conditions. You might need a graph, or might want to look at it to just kind of decide what's actually going to happen with this. So anyways, the integral test would look like this. Limit as b goes to infinity, and you'd end up with the integral from 1 to b. I would, if I were you, and I don't know if you did this or not, I would flip up right away. Did you guys discount the other integrand forms? You can tell it's not arctan. You can tell it's not natural log. It's sort of close to arcsine, sort of, kind of, but it's not. For me, flip up would make the most sense. The antiderivative of the inside is 2n, or excuse me, the derivative of the inside is 2n. So to work this antiderivative, we need to multiply by 2 and then multiply the outside by 1/2. So that would give us limit as b goes to infinity. And the antiderivative would be 1/2 times 2 times 1 plus n squared to the positive 1/2, evaluated from 1 to b. Make sense? We just proceed on with FTC 1. So it'd be limit as b goes to infinity, and we'd have 1 plus b squared to the 1/2 minus 2 to the 1/2. And as you think about what's going to happen as you apply that limit, it's going to be 1 plus a huge number squared, which just makes another huge number. And the square root of that would just be another huge number minus, it's just going to be a huge number, aka diverging, right? So you'd say goes towards infinity, therefore the series, I guess I'll put, therefore sigma from 1 to infinity of this also diverges, and your reason there would be, or your name would be integral test. So Sean, it looked like you were trying to do an nth term test. How'd that turn out? Oh, it's the never-ending radical up, down, up, down, up, down. Yes. That does happen. So the integral test is definitely better. Okay, cool. Gotcha. Do you guys have any questions? Okay, fair enough. We are going to then move on to what looks like a somewhat unhealthy test comparison. Comparing yourself to others is not always the best practice, but we're going to compare some functions. So, kind of in the narrative of us cheering for these little series to converge, let's think about how this goes. The nth term test is the super negative one, right? It only tells you that you're diverging, and if you're possibly going to converge, it says nothing. Geometric series test is very balanced, but it's very specialized, right? It only applies to geometric series. The p-series is also balanced, but applies to a pretty narrow chunk, right? Only the p-series go with the p-test. The integral test is also fairly balanced, but it has a little wider range, right? really the restriction there is that you have to be able to find the antiderivative of the integrand, right? So if you can do that, then the integral test will likely tell you something. It does have its conditions, though. And then we come to the comparison tests. So the comparison tests are very flexible, very adaptable. But for that reason, they're also kind of, it's kind of hard to find a valid comparison sometimes. Sometimes it's really easy. Sometimes it's kind of hard. So you might want to think of these as like the people whose morals are sort of relative, right? You know what I'm talking about? Like, well, hey, you're not that bad compared to so-and-so. Or, hey, you're pretty good compared to so-and-so. That's basically what these comparison tests are, right? We're simply just going to be comparing two things and making a judgment based on that. So, so the landscape gets a lot more broad here. Potentially, there's a lot more things that you could analyze with this. But as I mentioned, the key is being able to pick what I've put in here are quotes, a good function to compare with. So it needs to be something that you know stuff about, and it also needs to be something you can actually work with in comparison. So we're going to use a graph to kind of look at this. We did talk about this. Does this sound familiar? We did talk about this when we did improper integrals. We just talked about it a little bit. So the standard we're going to start off with here is let's say that a sub n is a series and it's positive, but it is also less than or equal to b sub n over the interval that we care about. So if we were going to draw a graph of this situation, the graph would look like this. So b sub n would be there, and a sub n would be down there somewhere. So a sub 1 is lower, is less than or equal to b sub n on the interval that we care about. So here is the comparison test. Sometimes this is referred to as the direct comparison test because we are going to look at a slightly different comparison test here, probably by the end of today's class, I would bet. So here it is. If b sub n converges, then a sub n converges. Let's talk about some loose reasoning why. Remember the convergence or divergence of series like this depends solely on how fast they get closer to zero, right? So the idea is if b sub n converges, that means b sub n is approaching fast enough. Well, if a is lower than it, doesn't a have to then by default also have to be approaching fast enough as well? Does that make sense? Since it's always lower, it'll be getting there even faster than the one that's higher. And then the other piece is if the lower series diverges, then the one that's getting there slower is getting there even slower than the one that didn't get there fast enough, so that one also diverges. So you can't flip these statements around. So in other words, you can't say a sub n converges, therefore b sub n converges. That's not a valid comparison, right? So if a sub n gets there fast enough, that doesn't mean that b sub n gets there fast enough either, because b sub n is higher. It might, but that's not a valid comparison. Okay, you could also say, hey, you know what? I figured out that b sub n diverges, therefore a sub n must also diverge. Also not a valid comparison, right? A sub n could go either way based on b sub n, the higher one, diverging. It makes sense? We're comparing. This one's higher than that one, this one's lower than that one, and based on what we know, we maybe can make a judgment. Let's see here. Yeah, that's basically it. You think you can start making some comparisons? Okay, cool. We'll take a look then at our examples. Okay, so let me lead you through a little bit of reasoning here and then I'll let you try. So it says use an appropriate test. Take a look at number 1. It says sigma from 1 to infinity of 1 over 2 plus 3 to the n. You look at this and you think about the nth term test. The nth term test is going to head towards 0, right? And so the nth term test tells us nothing, so we move on. We ask ourselves, is it a geometric series? Sorta, right? Almost. Like, what's the thing in there that makes it not really a geometric series? The 2, yeah, the plus 2 in there the 3 to the n clearly is a geometric element, but the 2 plus kind of muddies the waters somewhat. And it's not a p-test, right, because it's got a numerical base with a variable exponent. And integral of 1 over 2 plus 3 to the n, no thank you. As far as finding an antiderivative there, I think comparison is a good way to go. Okay, so you might have a sense, based on your understanding of relative growth rates and what geometric series do or don't do, you might have a sense of where this is headed as far as convergence or divergence. And so let's take just a minute or two here. Let's try to think about what might be a good comparison to maybe prove what your instincts tell you. So think it over. This is the hard part. Once you get a good comparison, it's actually pretty easy, but getting the comparison might be tough. So talk it over, think it over. What, you guys have any suggestions on a comparison? 1 over 3 to the n? Okay, I think that's a good comparison. I think it's a good comparison on a couple of levels. If we don't already know, we can quickly arrive at a conclusion for that one. And I think it's going to have a good relationship with the one we have up there. So let's start off with this. What is the relationship of your comparison? Like, how does it relate to the original? Is it always higher, always lower, or we don't know? Higher. Isn't it always higher? Yeah. So if you think how this would work, you could do some partial sums to kind of see this. So if you had 1 over 2 plus 3 to the n, if you started to run the series, you'd start at 1, and so the first term would be 1/5, and the second term would be 1 over 2 plus 3 squared, so that would be 1/11. If you did the third term, it would be 1 over 2 plus 27, 1/29. I'm going to erase all this stuff here in a second, so don't feel like you need to write this down. And then if you had 1 over 3 to the n, you started at 1, you'd get 1/3 plus 1/9 plus 1/27. So can you see that for every single term, the 1 over 2 plus 3 to the n, the denominator is always going to be 2 bigger, right? Is this making sense? This is the core of the reasoning. For the 1 over 2 plus 3 to the n, the denominator will always be 2 bigger than the other one. Therefore, if the denominator is always 2 bigger, the terms will always be a little bit smaller. Does that make sense? Okay. So you can run through that sort of reasoning in your head if you want. You can obviously write it out on paper if you want, whatever, but we want to get to that place. And if we do, we can say this, that 0 is less than 1 over 2 plus 3 to the n, which is less than or equal to 1 over 3 to the n on the interval that we care about, which is 1 to infinity. So that's that key relationship we got to state and recognize. This is going to give us our point of comparison to say one series is always less than or equal to or lower than or level with this other series. Make sense? So here is where we establish our comparison. I would say that sigma from 1 to infinity of 1 over 3 to the n is geometric, and r equals 1/3, right? And further, 0 is less than 1/3, which is less than 1. Therefore, what's the conclusion on that series? The common ratio is between 0 and 1. Therefore, that series converges. I'll just put the series converges. So then, therefore, we can say, therefore, the original series, sigma from 1 to infinity of 1 over 2 plus 3 to the n, also converges, and we're just using comparison to do so.
Would you say comparison, like by comparison test?
Sure, by the comparison test. Yeah, so like, I just want you to write down the name of the thing that you're using at this point. I don't know that that's going to be like typically a strict rule like on an AP test. So if you just use the conditions of the test, but you don't actually name the test, typically it's okay because you're still being logical. I just want to make sure that you're understanding the difference between the geometric series test and the p-series test or whatever at this stage of the game. So, and you can weave that into your answer, by comparison, blah, blah, blah. I mean, that's good too. Okay, so how you feeling? So comparison test, it's all relative, right? You're going to be comparing things. See what you guys can do with number 2. What'd you guys come up with? Anything for a comparison?
So we did 1 over n to the 1/2 at first, but that didn't help out, and then we just did 1 over n.
I like it. That's what I was thinking too. But in order to get a comparison, you're going to have to mess with that lower n value, right? You got to be careful with it. So consider, because you could conceivably make a false statement. Just mess around with what you need to mess around with, but I think that'll work. I do. Listen, I'm sure you guys understand why I had you just kind of wrestle with this for a little while, because it does require some thinking, and I heard good discussions and good thoughts, and I think we've arrived perhaps at a good place. To me, I'm sure there's plenty of others, but to me, the best one to use here. Did you guys come up with one? Not yet? You guys? Oh, go ahead. Say again. Close. So the hard part about that is that 1 over n squared converges, p-test, right? But then we'll find out that 1 over n squared goes below this one. So if you have, here, I'll just write it right here. If you have a series that converges, but then it's below another one, it doesn't really say anything about the one that's above it. It could go either way. So I'd say that you're really close. I would go with what these guys did, 1 over n. 1 over n, I think, is probably the best one. You're going to have to mess around with your lower value on the sigma, but I think that it works out okay. So I think if we did this, I think you can say 0 is less than 1 over n, which is less than or equal to 1 over 2 plus root n. But we got to be really careful on the interval that we use. On which interval is this true?
Which interval is that true?
Yeah. So if you did this, like if you just said, because you have to mention the interval, if you just said this, that's false. Because for a while, it's the relationship's the other way. So 4 is where it happens, right? So when n is 4, they're equal to each other. That's that intersection point. And so once you get 4, like above 4 on your n values, then this relationship is true. And so you just kind of fiddle around with it a little bit and just run some numbers in your head and be like, oh, look, 2 plus the square root of 4 is 4, and 1 over 4. Hey, look, they intersect. It might not always be as clean as that, but you just want to look at that. You just want to find an interval where that's true, and then you want to be able to say that that's going to be true for the whole rest of the graph.
Can you still use that then if you're using, like, starting at n equals 1?
Absolutely, because from n equals 1 to n equals 4, there's going to be a finite sum, right? It's going to be when n equals 1, then 2, then 3. And so then from 4 on out, if starting at 4 and then going to infinity, if we get convergence, well, then that finite sum is still going to converge, right? But if from 4 to infinity we see divergence, well, divergence plus some finite sum is still going to be divergence. I can draw you a graph here in a second if that doesn't make sense. Okay, so if that relationship is true, then we can say that sigma from whether you started at 4 or 1, it doesn't really matter, of 1 over n diverges. And you can do a couple different things here to confirm that it diverges. Here would be what I would do. I would say because it's harmonic, but you could also use a p-test with a p-value of 1 to say that that series diverges. You could also do a full-on integral test to show that that series actually diverges. To me, just saying that it's a harmonic series, that's the best way, right? You can just say it's harmonic, therefore it diverges. That's okay. And so because of the relationship we see up here, and because of the fact that 1 over n diverges, we can say, therefore, here's how we could chain it together if you wanted. You could say, therefore, sigma from n equals 4 to infinity of 1 over 2 plus root n diverges. Therefore, sigma from n equals 1 to infinity of 1 over 2 plus root n diverges. To actually address the question, this would be comparison, and because the convergence or divergence of the series does not depend on where you start the n value, absent any discontinuities of some kind, then if you just add on the n equals 1, 2, and 3 terms, it's going to have no effect on the convergence or divergence. It would definitely have an effect on the actual sum of the series, but not whether it converges or diverges. And this doesn't even have a sum, right? Because we're heading towards infinity. Okay, that makes sense? You did really well with that one. The fact that you guys came up with some really good thoughts about, hey, what if we did this? What if we did that? It's really awesome. Some people kind of get frozen, almost like, have you ever heard the phrase paralysis by analysis? Like there's like so many things to choose from. You're just like, oh, I don't even know where to start. Start somewhere. Oh, it didn't work. Start somewhere else. Oh, look, I see a relationship now. Here's what I should do. And that kind of thing. All right, awesome. I would like to do this, if it's okay with you. I hope it is. I would like to jump ahead just a little bit, and the reason why is I'd like to, tomorrow, I'd like to do number 3. I'd like to just space it out a little bit over 2 days so that you're kind of absorbing it right now. Maybe if we revisit number 3 next time, that would be a good way to do it. This right here, if I had to pick a favorite test, this one might be my favorite. This is called the limit comparison test. This one is actually new for the AP curriculum. I mean, it's established math, but last year was the first time that they made this an eligible topic. I like this one a lot, mainly for the perspective I can see it really easy, and I think this has the potential to make multiple choice questions that normally would maybe take you like 5 or 10 minutes to do. You could do them in like 10 seconds. It's kind of a cool thing. So if you have to do a free response version of this, it's not going to be that fast, but this comes in super handy. In fact, but even before this was a topic on the AP or the BC test, I always taught this simply because it made the multiple choice like boom, boom, boom. You'd get like 2 or 3 of them where you could just be like, done, and it's over with really, really quick. Anyways, so I think this is actually a pretty apropos statement. Sometimes it's difficult to establish a good direct comparison, right? You guys just spent like 5+ minutes like, what do we compare this to? I don't know. There's a struggle, right? And so sometimes that's really, really difficult. And in this situation, the limit comparison test might be the thing that makes it become actually really, really easy. So suppose that you've got 2 positive series, both A and B are greater than 0, and you run a limit of the ratio of those, right? So you do the limit as n goes to infinity, and it can actually be A over B or B over A. The ordering on the division doesn't matter. So you do the limit as n goes to infinity of one nth term over the other nth term, and you get some limit. Like you get a number, L. And L is positive and finite. So in other words, it's not infinity, and it's positive, right? So 2 would be a good one, or 17, or 2/9, whatever it happens to be. You get a positive and finite answer for that limit. Then that means that the 2 series that you're dealing with, both of them either converge or both of them diverge. So this is a comparison using a limit, hence it's called the limit comparison test. So the key here is to pick a series that you know about, and you're starting to get a decent library of series that you know about. And it has to have an nth term of the same magnitude as the series you are testing. We'll talk about what magnitude means here in a second. And I think this is an awesome substitute for the integral test. The integral test takes a little while, right? Because you got to set up an integral, and you got to confirm positive, continuous, and decreasing. And you got to find an antiderivative, and you got to involve a limit, an FTC1, and then eventually you get around to it. It's far from impossible. This is way faster, way faster. But just so you know, any quizzes you might have coming up in the near future, I do reserve the right to say, quote, using the integral test, blah, blah, blah. So please don't look at this as like, sweet, I'll never use that. I reserve the right to specify the method that you use at times. Other times I'll just be like, yeah, whatever is valid, whatever you think is appropriate, do that. But sometimes I will say that. All right, so let's take a look here at number 1, and I want to kind of take you through the thought process that you might go through for a question like this here. we go. So you look at this, and if you thought about an nth term test, can you guys see pretty quickly that the nth term of this series would go to 0?
Yes.
And so the nth term test tells us nothing. And then we think, all right, well, is this a geometric series? Nope, because you don't have a numerical base with a variable exponent. So it's not geometric. You can't use that. Is it a P series? Not a P series. You could. There is one faster way than what I'm about to show you, and that is, couldn't you identify that as a harmonic? That fits the 1 over an plus b perfectly. You could. So this would be the one way that would be faster for this one. You could say, hey, that's a harmonic series, therefore it diverges. So based on that, we know this is going to diverge. The integral test, very doable, but you're going to end up with an ln. You're going to have to use FTC1 and on and on and on. It's not necessarily going to be the greatest. Here's what I would do with this one. I would use the limit, or I don't know, I would probably use the harmonic thing. But if I didn't see that, what I would use is this limit comparison test. Here's what I mean by magnitude. What is the degree of the top? Nope.
No, 0.
Degree 0. What is the degree of the bottom? So what I want to do is I want to choose a comparison nth term that follows the same pattern, where the degree of the top is 0 and the degree of the bottom is 1. Or you could also say where the difference in the degrees is the same. I think that's probably a better way to put it. So the difference in the degrees is 1. So what I would say is I'm going to use sigma from n equals 1 to infinity of 1 over n. Right? So the degree in the top is 0. The degree in the bottom is 1. So the difference is 1. The truth is, if you wanted to just be strange and weird about this, if you really wanted to, you could say, hey, let's make the degree for my comparison. Let's make the degree in the top 17 and the degree in the bottom 18. And that would be just as effective. It's a little pointless, to be honest with you, but you just need the difference in the degrees to be 1. So here's how it works. There you go. Yep. I'm going to set up my limit. It's going to be limit as n goes to infinity of, I'll go 1 over 2n plus 5 over 1 over n. You basically just go limit as n goes to infinity of one series over the other one. And if you wanted to here, you probably would want to do this. Do a copy dot flop. So I'll go limit as n goes to infinity. And if you copy dot flop, isn't it just going to be n over 2n plus 5? Okay. So who's lurking in the wings right now? Somebody is just like waiting for you to discover them. Who or what? No. Much older person than that. Come on, do the limit. Who shows up? L'Hopital shows up, right? So if you try to evaluate this limit, you get...
Every time.
He's a lurker. He's always just like right there waiting for you to be surprised by him. Yes, the hospital guy. Yeah, so then if you actually do L'Hopital's rule, limit as n goes to infinity, wouldn't you just get 1 over 2? Yep. So equals 1/2. And then you'd want to recognize which is positive and finite. Finite. Therefore, here's where we come to our conclusion. I'm going to go back up to the top. Therefore, because sigma of 1 over n diverges, and there'd be a variety of reasonings for saying that that diverges. Therefore, because that series diverges, sigma from n equals 1 to infinity of 1 over 2n plus 5 also diverges. So let me just give you a hint about how this can be ultra fast on a multiple choice scenario. Actually, before I do that, do you have any questions on that one? Like if you're doing an open response, you got to kind of do all of that. Go ahead.
So why did you pick 1 over 10?
Yeah.
Because it matches the difference in the degrees. It's the simplest match for the difference in the degrees of the original. So the original was degree 0 over degree 1. So the difference between those was 1.
Right.
So 1 over n has the same difference in degrees, 0 and 1. Mm-hmm. Like I mentioned before, if I wanted to pick like n to the 20th over n to the 21st, has the same difference in degrees, but that's just silly.
What if
right?
you had like 1 over 2n? Is that the same?
You could do 1 over 2n, yeah. But then the hard part about that is you've picked 1 over 2n, and 1 over 2n, I guess it is still a harmonic, so you could probably still use that, but you want to go with the simplest conceivable comparison. That make sense? Like you honestly, you could have done like n to the 1/2 over 5n to the 3/2 has the same difference in degrees, but 1 over n is really, really simple.
Is that just part of the rule? You can just divide it?
That's what the limit comparison test is. Yep. You take your comparison of one series over the other series, and if you get a positive finite answer, then both series converge or diverge. And if you know one of them, that means you know the other one as well. So that's why you want to pick a known one. Hang on one second. I want to show you something I think will be super useful to you. Do you have any other questions on this one? Let me show you why I think this is super fast and super convenient for a multiple choice scenario. Take a look at number 2. Here's what I would do with number 2. If I were taking some test, some multiple choice test, and I didn't have to justify anything. If you have to justify stuff, then you got to do what we'll do with this one next time. Okay? But if this was a multiple choice test, I'd look at this and the question is, does it converge or diverge? Here's what I would do. I'd look at this and I'd say, well, maybe I'd run through the whole nth term test, blah, 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 but I'd arrive at this and I would say the degree of the top is 0, the degree of the bottom is 2, and so what would I compare this to?
1 over n.
I'd compare this to 1 over n squared. And what does 1 over n squared do? Does it converge or diverge? Converges, p-test, right? Therefore, that series converges too. So in a multiple choice scenario, you just look at the difference in degrees, say, hey, I'd compare that to 1 over n squared, converges, done. That makes sense? So potentially a really, really fast strategy for you. If it's open response, it's not that fast, but for free response it is.
Don't you have to make sure that the one is positive and finite?
Say again?
Or don't you have to make sure?
In a free response, yes, but I'm talking about multiple choice where you don't have to check your work. So you know what? I've got 5 minutes. Let's run through this one. So let's say we were going to do this one. We compare it to 1 over n squared. So I'll just make a note of that. Compare to sigma from 1 to infinity of 1 over n squared. So what I would then do is go limit as n goes towards infinity. And you just put one series over the other, and it really doesn't matter the order in which you do it. I'm just going to write 1 over n squared over 1 over 3n squared minus 4n plus 5. You do copy dot flop. Limit as n goes towards infinity of 3n squared minus 4n plus 5 over n squared. And you really don't have to use L'Hopital's rule if you don't want to. If you wanted to look at this, and couldn't you use the old pre-calculus degree trick?
Yes, I love that.
And if you do it right, hey, listen, if you do this whole limit comparison test right, shouldn't you always get equal degrees if you do it right? So then this would equal 3, which is positive and finite. So then all you got to do is go back to what does your comparison do as far as convergence or divergence? You come back up here and say this converges because of the p-test, p equals 2. Sorry, the 2 went off the edge there. Therefore, because our comparison converges and we got that positive and finite number for our limit, we can say that the original series also converges. So Caroline, you're concerned about, hey, we got to make sure that that number, like that condition is met. And I agree, and for your response, you absolutely have to do that.
That seems like it's always like.
Yeah, that's why I'm saying on a multiple choice scenario, that's why it's just like done.
So the other two.
If you pick a really bad comparison,
What would be a really bad?
one in which the difference in the degrees is not the same as the original difference in degrees.
So we did like 1 over n cubed.
Yeah,
But if the difference in degrees is the same, this should pretty much always work.
should.
Okay.
Yep. That's why I say it's like a super easy test, a super easy thing to use for multiple choice. for your response, I mean, you can see the space and time required is about the same as the other ones. But for your response, or multiple choice, it could be very quick. So you guys are seeing a good connection, for sure. And I mean, that's testing strategy stuff. I know we're not there yet, but that's what I was saying. Okay. I think that's a good place. We will finish comparing mañana, and I think we've got a quiz coming up next week. There's always a quiz coming up. Not this week. There was no quiz this week.
I was amazed by that.
Right? No quiz this week. How about that? Yeah.
Is it Monday?
It could be Monday, yeah.